4.1 notes are on an introduction to polygons. Polygons are plane figures. We have examples of some polygons here. Poly means many, so it stands for many-sided figures, and these four figures that are shown here are closed as well. The four figures that are not polygons have rounded edges, they overlap, and they're not one closed region like here and here, and then there's an open figure here. So those are all examples of what a polygon does not look like. Here are the names of several polygons. You already know some of them, but there are a few in here that we're asking you to remember. Like a 10-sided polygon is a decagon, and then if you know that a pentagon has 5 sides, then a 15-sided polygon is a pentadecagon. If you have to draw a polygon, you need to name it by using its vertices. We have a drawing of a pentagon here. If you want to say the name of this pentagon, you need to go around the figure using consecutive vertices. So we could call this pentagon A, B, C, D, E, or we could have gone in the other direction, A, E, D, C, B. But you can't skip around, so you can't say A, C, E, B, D. That is skipping vertices, so that is not a name for that polygon. Take a moment to draw the polygon STOP. Because there are 4 letters there, it will be a quadrilateral. So I'm going to just draw 4 sides, and when you put STOP on the vertices, go around counterclockwise or go around the figure clockwise, labeling it. What you cannot do is label it STOP. So the labels went like this across the middle of the figure. You need to be able to go around the outside of the figure, labeling the vertices. Diagonals of a polygon are segments that connect non-consecutive vertices. So the first one I could draw would go from here to here. If I went to a consecutive vertex, that would simply be the side of the polygon. So this is a diagonal. I could draw other diagonals from that vertex. I could draw that one, and that one, and that one. So there are 4 diagonals right there from that one vertex. You could move to another vertex and draw more diagonals. Here's a 5th, a 6th, a 7th, and an 8th diagonal. And you can keep going around the figure. When you get to a vertex, though, where there's already a diagonal drawn, you don't want to redraw right over it again. So you can draw in more diagonals from this new vertex. 2 more vocabulary words are opposite sides and opposite angles. Opposite sides are like the left and right side of this quadrilateral and the top and bottom. They're opposite from each other. Then angles, like the upper left angle, is opposite from the lower right angle. And then these 2 angles are opposite angles from each other. The word consecutive means the next one in line. So if we start at this top side here, the next consecutive side is here, then here, then here. So they're right next to each other as you go around the figure. And the same is true for angles. So if we start at this vertex here, let's call it A, and then we go to B, then C. Angle B is a consecutive angle to A, and then angle C is a consecutive angle to angle B. In this diagram, we have marked the interior angles of the figure with X's. The exterior angles of the polygon are created when you extend a side. So I'm going to extend this side of the polygon. This angle would be an exterior angle. Now we could have extended this side to go in this direction to get this exterior angle, which would obviously be congruent to the first one. But all we want to do is draw in one exterior angle at each vertex. So I'm going to go around the figure. I'm going to go to the left and extend the side, the next side, to create this exterior angle. Then extend the next side to create this exterior angle, and so on, going around the figure. And notice how they're supplements of each other. So if the interior angle is X, the exterior angle would be 180 minus X. So the exterior angle is supplementary to the interior angle. Here's a series of polygons drawn in a row. The first polygon, of course, is a triangle. I'm going to use the letter N to stand for the number of sides of this triangle. So in our first picture, N equals 3. In the triangle, we know that the interior angles add up to 180 degrees. And now we're interested in what the interior angles add up to in other polygons. In order to determine that, I can draw a diagonal in this quadrilateral. And that diagonal created two triangles. This triangle would have angles that add up to 180 degrees, and this triangle would have angles that add up to 180 degrees. So that means there are two 180 degree triangles in there. So that is a sum of 360 degrees for the interior angles. In the next figure, where the sides are numbering 5, I can draw in two diagonals. In the next shape, there are 5 sides, so N equals 5. And I can draw in two diagonals, creating 3 triangles. So this triangle's angles will add up to 180, these would be 180, and these would be 180. So I'm looking at 3 180s to find the sum of the interior angles, and that total would be 540 degrees. The next shape has 6 sides. I can continue doing this process where I break it up into triangles. And I know the sum of the interior angles of a triangle is 180, so that means this figure will give me 4 triangles for a total of 4 times 180 degrees. So the interior angle sum of that hexagon is 720 degrees. The last one we have is a 7-sided figure, which we call a heptagon. And if you draw in diagonals for the heptagon, you will see 5 triangles. So set up 5 times 180 and you will get 900 degrees. Look for a pattern between the number of sides and the sum of the interior angles. Notice how when N is 4, I need to multiply 2 times 180. When N equals 5, I need to multiply 3 times 180. When N equals 6, I multiply 4 times 180. So it's always 2 less than the number of sides. Look at the last one. There are 7 sides, and I multiplied 5 times 180. So that means the interior angle sum will be the number of sides minus 2 times 180. Try to use that formula now to determine the interior angle sum for each of the following polygons. I'll set up the first one. If a polygon has 9 sides, then the interior angle sum is 9 minus 2 times 180. So on my calculator, multiply 7 times 180. You would get 1260. Pause the video. Do number 2 and 3, and then turn the video back on to check your answers. The next formula is one of the easiest formulas we have in geometry. If we draw one exterior angle at each vertex and we add them up, the exterior angle sum is 360. So it does not matter how many sides there are, the sum will always be 360. And finally, we have our last formula. The number of diagonals in a polygon is given by the number of sides times the number of sides minus 3 over 2. Find the exterior angle and the number of diagonals for each of the following. The exterior angle sum is going to be 360. It will always be 360 regardless of the number of sides. The number of diagonals in a triangle can be calculated by taking the number of sides 3 times the number of sides minus 3 over 2. And you can tell it's just going to be 3 times 0 on the top. So there are no diagonals in a triangle. Number 5, the exterior angle sum of a 13-sided polygon is also 360 degrees. To find the number of diagonals, I'm going to calculate 13 times 13 minus 3 divided by 2. So that would be 13 times 10 divided by 2. 2 cancels with 10 and leaves a 5. So 13 times 5 is 65. There are 65 diagonals in a 13-sided polygon. Number 6. The exterior angles of a pentadecagon add up to 360 degrees. The number of diagonals can be found by taking 15 times 15 minus 3 over 2. 15 minus 3 is 12. I can cancel the 2 on the bottom with the 12, and that leaves a 6. 15 times 6 is the same as 30 times 3, which is 90. There are 90 diagonals in a pentadecagon. Now we'll do some practice problems using the formulas that we learned. A polygon has an interior angle sum of 1620. What would be its exterior angle sum? All polygons have an exterior angle sum of 360. Part B, how many diagonals does this figure have? Since we were given 1620 is the interior angle sum, I'm going to use the formula for the sum of the interior angles, which is n minus 2 times 180. So since that sum is 1620, I'll let 1620 equal n minus 2 times 180. The next step would be to divide both sides by 180. 1620 divided by 180 is 9. 9 equals n minus 2. Add 2 to both sides. The figure we're talking about is an 11-sided figure. That's an Untitled. To find the number of diagonals, I'm going to put 11 into the diagonal formula. 11 times 11 minus 3 divided by 2. 11 minus 3 is 8. Cancel the 2 with the 8. That leaves 4. There are 44 diagonals in an 11-sided figure. Number 8. The interior angle sum of a polygon is 900. We need the name of the polygon. The interior sum formula is n minus 2 times 180. Let's set 900 equal to n minus 2 times 180. Divide both sides by 180. 900 divided by 180 is 5. 5 equals n minus 2. Add 2 to both sides. The polygon has 7 sides. A polygon with 7 sides is a heptagon. Number 9. What is the name of the polygon with 9 diagonals? I'm going to let 9 equal the diagonal formula, n times n minus 3 over 2, and then I'll solve for n. Multiply both sides by 2. 18 equals n times n minus 3. Distribute the n. Subtract 18 from both sides. Let's factor that quadratic. 3 times 6 is 18. So I'll set up n with 3 and n with 6. 1 must be positive and 1 must be negative. 6 must be negative so that we get negative 3n in the middle. N is either negative 3 or positive 6. N cannot be a negative number because it stands for the number of sides of a polygon. So the answer must be 6 sides. The name of a polygon with 6 sides is hexagon. What is the interior angle sum of an octagon? An octagon has 8 sides. So the interior sum formula was n minus 2 times 180. So I'm going to put 8 in place of n. That means I need to find 6 times 180. That is 1080. Number 11 and number 12. I would like you to pause the video, try 11 and 12, then turn the video back on to check your answers. I hope you set 54 equal to the diagonal formula. The first step to solve is multiply both sides by 2. 2 times 54 is 108. Now distribute the n. Subtract 108 from both sides. Now we'll need to factor the quadratic. 12 times 9 is 108. Make 12 negative, make 9 positive, because you want them to add up to -3. That means n is 12 or -9. You know n cannot be a negative number because it represents the number of sides of a polygon. So n must be 12. The interior angle sum is n minus 2 times 180. So I'm going to use our n of 12. That gives 10 times 180, and that is 1800, our answer. Sometimes the polygons we work with are called regular polygons. A regular polygon is equilateral and equiangular. So we have some pictures of regular polygons here. We've drawn a regular triangle, a regular quadrilateral, a regular pentagon. Here's a regular hexagon, and here's a regular octagon. Do you remember that the sum of the exterior angles of any polygon adds up to 360 degrees? So I've drawn in the 6 exterior angles here to this regular hexagon. Knowing that in a regular polygon, all of the angles are congruent, you can take that exterior sum and figure out how much each of those angles adds up to. So here we go. Each exterior angle in a regular polygon is found by taking 360 and dividing by n. That would get you each of the exterior angles. And then, if you wanted each interior angle, you have a choice. You can find the supplement of the exterior angle, or you can use this formula, which takes the sum of the interior angles and divides by n. So that's what we have in these two formulas here. For the exterior angle, you can take the exterior angle sum of 360 and divide by n. For each interior angle of a regular polygon, you can take the interior sum of the polygon and divide by n. Let's do a few examples. Find the measure of each interior and exterior angle of a regular quadrilateral to begin with. A quadrilateral has 4 sides. N will equal 4. The exterior angle of a regular quadrilateral is 360 divided by 4, which is 90. For the interior angle, you can take that 90 and find its supplement, or you can do the sum of the interior angles divided by n. For a heptagon has 7 sides. So the exterior angle of a regular heptagon is 360 divided by 7, which can also be written as 51 3/7. The interior angle of this regular heptagon you can find by taking the supplement of 51 3/7, or you can calculate the interior sum and then divide that by 7. That would give you 128 4/7. Number 3, n is obviously 20. The exterior angle is 360 divided by 20, which is 18. The interior angle, you can find the supplement of 18, or you can do the interior sum divided by 20. I will do the supplement on that last one. Find the number of sides of an equiangular polygon if each of its angles is 144 degrees. So what I can do is I can find the exterior angle from this interior angle. So since the interior angle is supplementary, I can do 180 minus 144 to get the exterior angle. The exterior angle is 36. So remember the formula, the exterior angle equals 360 divided by the number of sides. I can put 36 in place of e and then solve this equation. You can cross multiply here. 36n equals 360. So n equals 10. Number 5, 156 is the interior angle. The exterior angle would be 180 minus 156, which is 24. The exterior angle is equal to 360 divided by the number of sides. So if you cross multiply, you get 24n equals 360. So n equals 15. Number 6. This should read 172 4/5 degrees. Sorry about that. Let's find the exterior angle. 180 minus 172 4/5 would give us 7 1/5. That could also be written as 7.2 if you're using your calculator. 7.2 equals 360 divided by n. So if I cross multiply, I get 7.2n equals 360. Divide both sides by 7.2, and the answer is 50.